All right, so in this video lesson, we are going to study about the partial derivatives of a multivariable function. Okay, and so the skill that we are about to learn here, the knowledge, the understanding we're about to learn in this particular video lesson here is admittedly focused on functions of two variables. However, any skill that's learned through the lesson here can be easily extended to functions of three variables or even more. Okay. And so let's now get to it. All right, so allow me to introduce the reason that leads to the problem right here. So let's start out with a given function, and the function here, I'm not going to bring in any specific example yet. I am just going to say we start out with our function given, some function f of x, and as I said earlier, it's a function of two variables. Okay, so with a function f of x comma y, f of x comma y being a given two variable function. Derivatives, the title, the topic, the discussion title was saying partial derivatives, but derivative is mainly to find instantaneous rate of change. Okay, and so now let me bring up two pictures. This function f of x has a graph as a surface. So allow me to demonstrate that surface as following. So it has a graph as a surface. Okay. And then I am going to pick a point. So at a point, at some point a comma b on the x and y floor, this point has a vertical value that create a point right on the graph, right on the surface. Or maybe let me put the point a little bit up here so that it's more trivial. Now it's all 3D perspective, so I'm not the best artist here. Okay, so that's the point. Allow me to duplicate this picture right here, make an exact duplicate version of that on my other board, because I need two pictures at the same time. I mean two copies of the same picture of the same function here. All right, so I'm trying to be as close as I can right here, but this is once again the graph, the surface that represents the graph of our given function f of x comma y. Okay, and once again right there at that point a comma b on the x and y floor, we have a point right on the actual surface itself right here. Okay, so now that means when it comes to instantaneous rate of change, again, derivative is to study instantaneous rate of change. Instantaneous rate of change. And that is no doubt about it. Anytime we're looking for the derivative, the main motivation is to find instantaneous rate of change. So now instantaneous rate of change, but a little bit unlike the kind of instantaneous rate of change we were doing in the old days, meaning the single variable calculus. Now at one point right here, think about on this surface right here, at one point at one point right there, as far as looking for rate of change right here, there are actually, and for a function of two variables, there are two instantaneous rates of change here indeed. Okay, and now let me show you what I mean right here. Think about right there at that point on the surface being the graph of this function. We can draw the tracing curve. Now, so back in the days, back in the lecture where I showed everyone how to make a hand sketch, I introduced the idea of using the tracing curve right here. So right on that point, this point on the surface belongs to a tracing curve. So how about the tracing curve here? I'm going to draw the tracing curve that's parallel to the x-axis. So that's the tracing curve right there. All right, and so with this tracing curve, that point right there has a tangent line. So now, ladies and gentlemen, this tangent line right here at that point, this tangent line, but you gotta again take my take it closely with my the explanation here that this tangent line is only along the tracing curve parallel with the x-axis. Okay. And the tracing curve goes through that point, of course. But so in that way, this tangent line is the instantaneous. It is the instantaneous, but the instantaneous rate of change only with respect to this line. I mean, with this tracing curve parallel to the x-axis. And so for that reason, we refer to this as the slope, the tangent line there, and the slope of the tangent line. Yes, we refer to that as the derivative of the function f. But now in respect to or along the x-axis. So here in this case specifically, let me make a note here. We're looking at that tracing curve along the x-axis. And that's why along the x-axis we have the tracing curve there. And then so right at that point we do have a tangent line at that point with slope f sub x. So at this point, as I'm writing it here, I also shows everyone the formal notation for that. Now, this is not that formal yet, but formally speaking, it's f subscript x in parentheses x comma y. Okay, but ladies and gentlemen, this is called the partial derivative of the function f. Partial derivative of the function f in respect to x. In respect to x. Okay. That meaning it's along the tracing curve that's parallel to the x-axis, or along, for short, just along the x-axis. All right, so that's the meaning of the symbol, or for short, you can, okay, the short version is f sub x right here. That's the short version of that. So now in the way how I'm explaining, right at that point there was a tracing curve along the x-axis, and we had a tangent line, and the slope of the tangent line produced the f sub x for us, the partial derivative in the x-axis along the x-axis. So now the same picture, and now this is the reason why I created the exact copies, the two exact copies of the same picture over here. The same point, the same picture, right at that point. We can surely have a tracing curve that is parallel and along the y-axis, and my picture is right here. Okay, so this is here, this is along the y-axis. This is along the y-axis. So along the y-axis, that same point has a tangent line too. And again, forgive me if I'm not making the best picture of the tangent line there, but there's a tangent line supposedly tangent to this curve, this tracing curve along the y-axis, right through that point there. And so the slope of this tangent line, yes, we refer to that, ladies and gentlemen. It's the partial derivative of the function f, but in respect to y this time. So we use a subscript y indicating it. And then formally it comes with the notation indicating the pair of inputs x comma y right there. Okay, and I will get back further and explain why we still have to attach the x comma y thingy here. But then the short version of that, okay, the short version of that is just f sub y. It's just f sub y. And so now, as far as verbally as a name right here, this is called the partial derivative of the function f in respect to y, or along the y-axis right here. And then the meaning is exactly similar with the meaning of the f sub x that I introduced earlier. Okay, and so notationally, aside from this notation right here, the function with the subscript indicating partial derivative, we also have a different way of making notation for this. The partial derivative, think about our function here in the beginning. Think about our function is written as in equation form. Z equals that function f of x comma y. If our function in the beginning was written in the equation format here, then the alternative notation here, see, we're so familiar with dx, I mean dy, dx, and dz, dx. Z is a function. X and y are the two variables. So if we're writing dz, dx, that's close enough. That's close enough. It's indicating, this is the Leibniz notation right here, indicating it's a derivative, taking z as a function and taking the derivative in respect to x. But now, precisely speaking, to indicate that this is This is a derivative. To indicate that the function has more than one variables aside from the x, we don't use we don't use just the plain old dx dz anymore. Dz dx. We don't use that because this will give people the understanding that hey, x is the only variable in the function. But now instead of using that, we use a descriptive d right here. So this is d. It's still a dz. Okay, indicating z as a function. Descriptive dx. So we're still reading that verbally dz dx, but now with this way of writing descriptive d right here, it's indicating that it's the partial derivative of the function z in respect to x, and the way we're using the partial derivative symbol here is indicating that there are other partial derivatives from the same function aside from this dz dx. Okay, so bottom line is f sub x or dz dx. That's the two different ways how you can write the symbol for a partial derivative in respect to x. So in that way, similarly, f sub y is the formal symbol, but you can also write this as dz dy right here. But it's so instead of going with this plain old regular dz dy, we don't do that. Because doing this, the count one people will understand, and actually the people worldwide will understand that this function z has only y as the variable. But nope, this is the correct symbol for that, indicating that this is the derivative, the partial derivative of the function z in respect to y, because it's indicating that there are other variables aside from y in our function. So there you go, two different conventions of how we write the partial derivative, two different ways of writing the notation. Okay, so by far that introduces what it is to be the partial derivative. So in the end, this f sub x here is the instantaneous rate of change in respect to the x direction, whereas the partial derivative in respect to y means the instantaneous rate of change of this function right here. So right at that point, at that instance, there's a change in respect, there's an instantaneous rate of change in respect to y. At that instance being the point on that surface right there, there's an instantaneous rate of change in respect to x. Okay, and that's once again concludes what it is concludes our understanding of what it is to be the partial derivative in respect to x. In respect to x or y and whatever. And so our function here, another thing to keep in mind as a remark here, our function here ends up with, our function here is given at start here has two variables. So I am expecting two partial derivatives. And so now, like I said earlier, right before we began here, then the understanding here can be easily extended to function of three variables, function of four variables. So if we're looking at f of x, y, and z, then there will be, f sub z, f sub k, f sub s. Okay. For example, if we were given a function but of three or even more variables, four variables here, for example, then I am expecting first in line four separate partial derivatives. And of course, with a function of three variables or more, as I have explained already in my earlier lectures when I was showing the graph, then we cannot draw the graph here. We cannot generate the graph of a function three variables or more. But here we can still have f sub y, f sub x, f sub y, f sub z, f sub t. We can have as many partial derivatives as the number of variables being involved in your function. And that's another bottom line about what it is when we introduce the meaning of our partial derivative. All right, so now enough with what it is, enough talk with what it is, to be a partial derivative, and now we have a nice, good, detailed enough understanding. How do we find one? How do we find one? So, in a way how I drew the picture earlier that sadly I had to erase. Now, this is where we bring back our count 1 understanding, our beginning calculus understanding, our differential calculus, the usual calculus. We have to go through, anytime we're inventing a new derivative, we have to go through the limit definition. So let's say with a given function, and this time allow me to provide an actual function so that I can demonstrate the idea of how we find it. And along the way, as I'm going through this demonstration problem, this example problem, you will understand the way how we're doing it. So how about the problem here is we have x squared y xy squared indeed plus x cubed y. We have for ourselves at start a function, 2 variables, xy squared plus x cubed y. So back to what I said earlier, we're about to learn through this example how we can find the partial derivatives. Our function here in particular given to be 2 variables. Okay, so I am expecting to find 2 partial derivatives. There's the fx and there's the fy, f sub x and there's f sub y. Partial derivative in respect to x, partial derivative in respect to y. 2 separate partial derivatives. So I am going to demonstrate one. Let's look at f sub x right here, the partial derivative in respect to x. How are we going to find it? The real truthful fundamental is that we have to go through the limit process. We have to set up the following. Now, keep in mind that we're right now targeting the x as the main variable. We're targeting x as the variable. So this is how we set up the difference quotient and go through the limit process, just like how we were learning that back in calculus 1, the beginning differential calculus. So now our function here, I'm going to go f of x plus h with the second variable comma y. See, I don't need to do the plus h for y because right now I am looking for the partial derivative. As I spelled out loud earlier, I am learning how to find I'm showing how to find the partial derivative in respect to x. That means we only focus to the x variable. So the x variable here gets the plus h. The y variable, we leave it the same. Okay, however it comes with the function, that's how it comes with the function. The difference quotient is to be subtracted. The difference here is to subtract f of x comma y. And then we divide it by h. So this is how I say that I can always say that we extend the exact concept we've learned back in Calc 1 in the beginning differential calculus into this, and that the limit concept. If anyone took classes with me for Calc 1, this limit process here to take a limit is so important that I always emphasize that clearly. Okay, and now with this h parameter right here, we are going to take the limit allowing h approach 0. And anyone learning from this video lesson should also put this in a box. I'm about to apply this into this function. I'm about to apply this into that function. Okay, but this is one fundamental, independent with any function. So any function, if you would like to find the fx, you have to go through this formula. All right, so now from this point on, let's see how we can go further. So fx for this function in particular is going to be the following. Okay, so fx plus h, so I am going to substitute the expression x plus h into my x input variable and leaving the y exactly the same. So my function, or in other words, f of x plus h comma y will come out as following. X plus h multiplied with y squared, okay, because we substituted x with x plus h, all right, plus x plus h cubed times y. This completes our f of x plus h comma y. That's the function. Okay, and then the difference here is indicating that we're going to subtract the exact function. So x y squared plus x cubed y. That's how I'm putting in f of x plus h comma y subtract f of x comma y. Okay, and that difference there, I'm going to create a quotient with just simply h in the denominator. And now I will take the limits, but for now the limit process doesn't start yet. It's just a reminder that in the end this problem will be a limit problem. It is overall a limit problem, but we have to work with some algebra here. So all of that Calc 1 experience, as I have said earlier, will come back here, will need to be brought back here. Okay, so I have enough space here to write down one more step. So now we're going to take some algebra. So, and at this point, for anyone learning with me in this lesson, I do have my reason to expect that your algebra is decently good enough so that I can pick up the pace here on the algebra work. Okay, so I'm going to distribute the y squared term. So the first group here becomes x y squared plus h y squared. And then this cube right here, this cubic of the x plus h, I can expand that out as x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, and then we're going to multiply that with y. All right. Should have used brackets here. All right, and then I'm going to subtract, and then sign change here is going to happen. So xy squared minus x cubed y. So that's how I'm going a little further into that numerator of the quotient. And of course, I have to indicate that reminder here that it's in the end a limit problem. And now for the next step. And of course, you can, as you watch along with this video over here, you don't have to wait for me in every step. If you are strong enough in your algebra, you are more than welcome to advance ahead of me. Okay, so in the next step, I can go ahead and reduce my numerator further. So I have xy squared plus hy squared plus, I'm going to distribute that y right there. This y right here, I am going to distribute that for each term inside of my parentheses there. So in that way, I'm looking at x cubed y plus 3x squared hy plus 3xh squared y. Okay, and then plus h cubed y, and then minus xy squared minus x cubed y. That's the numerator after all of the work expanding out all the terms there, and we're still dividing by h. And this is a limit problem. That's just a constant reminder. We are letting h approaching 0. And then in the next step, I'm going to continue to simplify that. And at this point, I'm going to start seeing a lot of cancellations. So minus xy squared will cancel with this xy squared. All right. The minus x cubed y, there's the opposite term right here. We can cancel those out. Okay, so the remaining terms is h y squared plus 3x squared hy plus 3x h squared y plus h cubed y here. Okay, and now the fraction bar doesn't need to be extended as long. All right, and it's a limit problem still because we're still only beating around the bush right here. But now we keep getting closer. So taking all the exact, all of those exact experience from count 1 here, the next step it looks like we're gonna have to factor out the h common factor over here. So I'm gonna factor out the h, and I have y squared plus 3x squared y plus 3x h y plus h squared y, and divide all that here by h. Okay. And so, of course, the whole point of factoring out the h here is so that we can cancel the h. So in my next step, we have the remaining, we will reduce this entire fraction into something that has no denominator. Okay, it's a good thing that we've done that. So y squared plus 3x squared y plus 3x hy plus h squared y. But now we really are ready to take the final limits, letting h approaching 0. Okay, and then taking the limit on this function, it has y variable, it got x variable, and it has the h variable, and the h is the one that we focus to, letting h approach 0. So as we let h approach 0, that term remains the same because it's independent with h. So I have y squared. That terms remain the same because it's independent with h, 3x squared y. These two terms all have h factor in it. So as h go to 0, these two terms approach 0. So that's our final partial derivative. So ladies and gentlemen, I call this is our partial derivative in respect to x. The partial derivative of this function that I introduced in the beginning, this example function right here. Xy squared plus x cubed y over, the partial derivative we found on the other board at the final answer. All right, so in that way, what about, and we can see that we can similarly do the same thing. So now f sub y, the partial derivative of this function in respect to y, this is the setup, the fundamental setup right here. We're taking a limit, allowing h to go to 0, of a quotient as following: f of x comma y plus h. See, now we focus to the y variable to find the instantaneous rate of change. So the y variable in our two variable function here gets that plus h right there. And then we're going to subtract f of x comma y as usual. That's the difference. And then it's a quotient, difference quotient. Okay, so this is the fundamental, not only for this function, for this particular example, but this is the fundamental. Any time that we're finding a partial derivative, this is what we go through. This is what we go through. Okay, so I am going to leave it for viewers and students of mine to take this particular problem right here, FYT, for your own trying. Okay, I want you to calculate f sub y, and the work is going to be extremely similar to the work I've done earlier. Okay, we're just simply going to apply this fundamental, this formula into our given function. Go through the difference quotient and reduce down the terms and the denominator, and eventually take the limits as h go to 0. And that's how you're going to find it. So feel free to pause the video and make your own work. And then I will only give out the final answer. Okay. So assuming that you have already found, pause the video and work on your way up and found the final f sub y right here, the partial derivative in respect to y, the answer should be 2xy plus x cubed. Okay, this is the answer to that, and that is what I call that the f sub y, the partial derivative in respect to y. Okay, and then you can compare with your answer like that. All right, so that's even though it's not a formal example, that FYT here was a good place for you to practice your own skill already and going through that limit process like that. Okay, but now let me look a little further here. F sub x, the partial derivative in respect to x that we found earlier, the answer is still here on my board. Y squared plus 3x squared y. Okay. In the end, it's not the exact same function in the beginning, but it's another function of two variables, x and y involved. And that is the reason why formally I wrote earlier f sub x with, in parentheses x comma y. Okay, but like I said, usually for short we just write f sub y, and that's good enough. But this is the formal symbol. But now I kind of explain the reason why we have to have that notation in parentheses x comma y, because it's indicating that a lot of time these general derivatives we're finding, they are general derivatives, that they are functions of x and y. Again, they are another function of x and y. Okay, so in that way, similarly, this f sub y right here appears to be a function. Okay, a function in terms of x and y. And it's different with the other function that you have seen. It's different. It looks different with f sub x that we have found earlier. Okay, nothing guaranteed that these two are equal. All right, but that's formally how, and explains how. Why a lot of times it's you see textbook authors write f sub y but in parentheses x comma y, because in the end these are all functions of those two variables that already existed. All right, and so now I'm gonna get on my other board right there and put the two partial derivatives a little further so that we can recognize the point now is that we don't want to always go through the limit process for every single partial derivative problem. Okay, it's a big topic and it's a big skill that you have learned, but expectedly you are going to be doing a lot of partial derivatives, so we don't want to go through this process every single time we're finding a partial derivative, and so there has to be a way, and then I'm about to show that way of how we can quickly find a partial derivative without going through the lengthy limit process, even though the lengthy limit process here is the ultimate fundamental formula, the fundamental work right here. All right, so on my board, I'm still leaving that f sub y that we have found earlier. F sub x we have found earlier. And now f sub y that I have found was 2xy plus x cubed. Our beginning function. Okay, our given function was, the function itself was x y squared plus x cubed y. Okay, so let's compare the beginning function and f sub x right here, partial derivative in respect to x, to see what happens here. So f sub x here, it looks like, you see, it looks like the shortcut trick for this is that just like the days that we were doing derivative, then we got power rules. So x here was a power 1. So, and in respect to x, so that means here's the thing. If we're taking the derivative in respect to x, that means I'm going to regard these other variables. I'm going to regard the other variables or the other variables as coefficients. So that means here in this first term, the variable that really matters for now, because we're taking in respect to x, the variable that matters for now is the x variable. It has power 1. It has coefficient. This is coefficient. That's what we are currently regarding the y variable as, because we are taking derivative in respect to x. All right, so that's the rule. If you're taking the derivative in respect to one particular variable, you're going to regard all of the other variables as coefficients or constants. Okay, so now in this term, the y squared that comes along with that, that's a coefficient. So that's why power rule, as usual, says you multiply the power down by 1. Okay, and so that's why you got 1 times x to the 0 power, the power rule as usual, and multiply with y, the coefficient. And then, so again, just like that, next term, okay, and the sum of the difference rule back in the days we learned about derivative applies here too, okay, and so that second term right here, x is the one that we're targeting, so the power rule is going to apply for that. The y variable here is being regarded as a coefficient. And that's why, just think about if that could have been a 2 or a 5, then we're not going to have 5 times 3x squared. So here is 3x squared, but we times with that coefficient, y. And that's how we're ending up with f sub y equals to x to the 0 is a 1. That's why the first term is a y squared plus 3x squared y. Ladies and gentlemen, that's how we find partial derivative in a fast way, but now officially accepted. Okay, it's a formal way that's officially accepted and taught worldwide. That's how we take the partial derivative. So, what about the other one? Yes, it's exactly the same. And sadly, I'm out of space here, so I have to erase the work that we've had for the f sub x. F sub y is going to be treated the same way. Okay, so just keep in mind that our purpose now is to focus on to target on the y variable from our beginning function. So now in the first term here, and so you have seen earlier in my just now explanation, then term by term taking derivative is going to hold. You can sums the difference rule in taking derivative, okay, and constant coefficients and all that are all going to apply. Everything you've learned back in Calc 1 is going to apply. And so that means looking at the first term, now I'm treating the x here as the coefficient. Because now in this current work, the y variable is what matters for us. So the power rule says 2 multiplied down, so I have 2 times the coefficient x times y with power reduced by 1, so 2xy, 2xy. Okay, and then moving on to the next term, and sum rule allows me to move on to the next term. Here's in that next term, x cubed is the coefficient. That's the coefficient. Okay, only y matters, and y has power 1, so that's why we have x cubed. X cubed, because the power 1 here multiplied down, okay, and y to the 0, we have just 1, so that term right there is x cubed. That's how we have that. That's how we take any partial derivative quickly and correctly without going through the limit process. Okay. All right, so let's now get into doing some problems as examples so that we get comfortable with how we work with that. So now in an example that I'm introducing here, the instruction of my example is as following. Let's find all partial derivatives of the given function. All right. Now, my instruction for this, look at the way how it's worded. In this instruction, I want to find all partial derivatives. And I mentioned that earlier. If a function is given as a function of two variables, then all partial derivatives means we have two partial derivatives to find. If a function is three variables, then we're going to have, all partial derivatives means we're going to have three partial derivatives to find. And we will get to that. So, how about I'm going to introduce two little function right here. So one given function I introduce as part A of this current example. So how about f of x comma y is a function of two variables for now. So now, see, finding all partial derivatives means that I am expecting in this work, part A, fx and fy, f sub x and f sub y. Okay, so my f of x and comma y here is x squared e to the y. Okay, x squared e to the y. All right, so now getting into it, see, like I've been explaining, all partial derivatives. First thing I'm going to find fx. Okay, so fx here, f sub x right here, the partial derivative in respect to x, and of course it will be a function, a general function in respect to x and y again. Of x and y, but for short it's just fx. So just like the explanation, and here I am not going to ask anyone in this example to go through the limit process. And that's the point. We have already learned the quick way to bypass the limit process. So here, you got x squared, there's the x variable, there's a y variable involved in this exponential function. So I'm going to treat this here as coefficient. So all of that component there is coefficient. All right. And so now I'm looking at, so what matters for us here is just that, x squared. So it's 2x times the coefficient e to the y. We are done with f sub x. That's how easy and how simple that is. Okay, because doesn't matter how complicated looking that is, once we regard all of that here that involves the y variable, okay, as a coefficient, then all it matters here is just the power rules, multiply it down to power 2 and reduce that power by 1. 2x e to the y. And so now we can start, I'm going to speed up a little bit. F sub y here, okay? The entire term right here, it's a product. This part right here is the coefficient, all right? This is the coefficient. What we really have to take the derivative is this part with the y. So really coefficient stays the same, x squared. That's why x squared stays the same. Taking the derivative of e to the y in respect to y is going to be e to the y again, that we have learned back in the beginning differential calculus. So that's how I have found f sub y. All right, so that's it for this part A of our current function right here, of our current example right here. All right, so what about part B of the example? I'm going to introduce another problem. So how about this time g of x, y, and z. All right, so I keep having this advice earlier that Any skill that you've learned, yes, admittedly, I'm giving the instruction on mostly focused on functions of two variables. But any skills you've learned so far can be easily extended and applied to functions of 3 variables, functions of 4 variables. So right here we have a function of 3 variables. So the instruction of the problem again says we want to find all partial derivatives. Okay, so this function g I'm about to write down has 3 variables. So I am expecting or expect ahead of time that we will be going to find gx, g sub x, g sub y, and g sub z right here. We're going to have 3 partial derivatives for this function because it's got 3 variables. Okay, so the function given is in here. How about is given as following: y times sine of x z squared. All right, y times sine of x z squared. Okay, so now let's go to find that one by one. We're not using the limit definition. Gx, okay? So we focus on x right here as a variable. Everything else is coefficient. All right, so now I'm going to look at y is a coefficient. See, coefficient. All right. But now the function, the x variable is inside the sine function. It's inside the sine function. See, it's this coefficient z squared is the coefficient for x, but the whole x z squared is inside the sine function. So we have to bring back the chain rule. So I purposely brought in this problem so that to make anyone learning from this lesson realize that anything you have learned back in count 1, including the chain rule, has to be used here. So now the chain rule says we have to take the derivative of the outside function. All right. So the derivative of the outside function here gives me cosine of x z squared. Okay. X z squared. But now I'm going to multiply with the derivative of the inside. The derivative of the inside now focusing on the x as the main variable and leaving z squared as the coefficient. And here I'm looking at multiply with z squared. So now my final gx here is about y z squared, putting the variables together, times cosine of x z squared. All right, that's how we're done with gx. So gy is going to be done similarly. We're not going to use the limit definition, the limit process right there. So I am going to clear out some of these extra notation. Okay. All right, so let's observe our function one more time. So in this function, we want to focus. In order to find gy, we want to target on y as our main variable. Everything else that's involved, other variables, any other variables, okay, any other ones of the variables is going to be regarded as a coefficient. So the entire, surprisingly, believe it or not, the entire sine of x z squared here can be regarded as a one huge chunk of a coefficient. Okay. And so in that way, the variable we have is here. So that means power 1 multiplied down, reduce the power by 1. We got just simply sine of x z squared. We are done with g sub y. That's how simple that is for that. Okay, so g sub z. What about g sub z? All right. So at this point, you can start advancing ahead because you've seen all of that experience right there. Okay, you can start moving ahead of me right here. So z is our main variable. That is a coefficient. So the work for doing this is very similar to the work I've done for g of x right here, for g sub x. So now I'm looking at y as a coefficient. Chain rule has to take place here. So the outer function is cosine. The outer function is sine. So taking the derivative, we have to take the derivative of the outer function first. So cosine of x z squared. Okay, but now I'm going to multiply with the derivative of the inside in respect to z. So in respect to z, we're looking at 2xz. Okay, and then writing that in a little bit cleaner form right here. We're looking at 2 x, y, z multiply in front, and then there's a cosine of x z squared. That is your g sub z, ladies and gentlemen. So that's how we have found the g sub z. Okay, the partial derivative in respect to z. All right. And so my point of bringing in this particular problem here is just to emphasize again that be aware that the chain rule applies again too. So in the earlier examples, all the fundamentals, basic derivative rules, the sums and difference and taking powers are all here, right? Power rules for taking derivatives are all here. And then further on this particular example, it's not only to show that we can extend our understanding to function of 3 variables, but we can also realize that, hey, the chain rules back in the old days still apply here. Okay, still applies here. All right. And so now let's look at another example. So here I would say let's evaluate the partial derivatives okay, plural again, the partial derivatives of the given function about f of x comma y to be x y squared plus x cubed y, okay, at 2 comma 1. Okay, so admittedly, before we get into this, doing the example here, this is that function I brought up earlier as the demonstration example, so that it shows everyone how to find the partial derivative using the limit process like that. But now we already had and we already learned the more efficient way, but it's still going to be in the same function. What I didn't do earlier in that demonstration with this function is that I didn't evaluate, because recall for yourself, we already found f sub x in terms of as a function of x and y. That f sub x here was y squared plus 3 x squared y. That's f sub x. Okay, and it's in the end it was a function in terms of x and y. It didn't have a value, it was just an expression in terms of x and y. Okay, and then f sub y that we found earlier in the demonstration example on this function, we found that to be 2xy plus x cubed. We found that. But in the end, we didn't have a value because it was just a general expression. So now we're going to go ahead and proceed into, see, partial derivatives. We got 2 partial derivatives. That means for this particular example, I want to substitute this particular point on the x and y floor. 2 comma 1, 2 for x, 1 for y. I'm going to substitute that value into the partial derivative I have already found in respect to x. So that means now just straight old, plain old calculation that's going to come out. So we got 1 square plus 3 times 2 square times 1. Okay, and the calculation will come out easily for this to be 7. All right, so let's take a quick pause here. What does that 7 mean? What does that 7 value mean right here? It means, so recall the picture. This function has a graph that being a surface that may look like this. Okay, 2 comma 1 is a point about here. Okay, 2 comma 1 it on the x-axis. So 7 right here means on the x and y, along the x-axis. That's what I mean. We have a tangent line, on that tracing curve along the x-axis. We have a tangent point at 2 comma 1. Okay. And of course, my picture is a little bit inconsistent with the results here, but that means the slope of this tangent line is a positive 7 right at that instant. The slope, the instantaneous rate of change of this function along that tracing curve, okay, is being positive 7. Now, and so again, I apologize that I drew the picture here to be a little bit inconsistent with the final numerical result like that, but that doesn't violate the understanding. Okay, so now similarly, once I have the given point 2, 1, f sub y at 2, 1, that's what we're really asked to find right here. Then I am going to substitute 2 for x and 1 for y. So 2 times 1 plus, okay, 2 cubed, right? That makes an 8 with a 4 more right there. That's the total being 12. Okay, so just like that. So that means on the same picture here, and again, it's starting to bother me a little bit, but it's okay because a lot of time it's hard to draw the actual graphic there. Okay, so we have a picture, the point. Okay, so the curve that goes through the tracing curve is like that. All right, and so the tangent line this time, yes, it does look rising. Okay, so on that tracing curve parallel to the y-axis, x-axis, on that tracing curve specifically containing that point 2, 1 on the surface right there. Okay, that tracing curve has tangent line at slope 12, positive 12. Or another way of seeing it, it's the instantaneous rate of change of this function, okay, at that point on the surface being 12. All right. All right, and so now let's look at some higher order partial derivatives. So we're still studying about partial derivatives, but let's consider the higher order cases. Okay. So for short, allow me to say higher order partial. Well, can't be any shorter anyway. Higher order partial derivatives. Okay. It's a one small subtopic right here. All right, so, and allow me to give the instruction to the teaching based right on that example we've had earlier. So f of x comma y was given, I'm using again that exact same demonstration example we've had earlier. Xy squared plus x cubed y. We have already found, and I'm going to split that into 2 columns. We have already found fx, okay, as a function of x and y, being y squared plus 3x squared y. And we also found f sub y being 2xy plus x cubed. Okay. Higher order derivative, forget about partial. Higher order derivatives just means we find the next derivative, the second order, the third order. Okay, second derivative, third derivative. So now, but with the partial thingy, now let me ask you, ladies and gentlemen, and you will click right here. If we already have fx right here, okay, do you think you understand this symbol? F sub x means y squared plus 3x squared y. Do you think you understand this symbol after my hopefully thorough enough explanation of these subscripts means, what these subscripts means? All right, then in that way, it means what right here from this f sub x, right here from that f sub x, we're going to find an additional partial derivative because it's a function of 2 variables. We find another partial derivative in respect to x. All right, so as easy as it can be. Okay, no need to make anything overcomplicated. That term is a constant, so it goes to 0. That term has x here, so it's 6x, y. The y here is the coefficient. That's how we find the partial derivative. This is the second partial derivative, second order partial derivative. See, we take f from the function, we take f sub x first, that's why it has that here, and then we take f sub x again. So the order here does matter a little bit. This x is the first order, and then the second order is that x. Because the reason I'm mentioning, because now what do you think, or do you think you understand what this symbol is asking you to do? F sub x, y here. All right. take it simple. F sub xy means from what we have already found f sub x, we're going to find the second derivative in respect to y. We take one more derivative, but treating y as the main variable and leaving 3x squared as the coefficient. So that becomes 2y plus 3x squared. That's how I have found the second partial derivative after f sub x. This is f sub xy. So the order here is at the order of the work. We found f sub x first, and then on top of f sub x, we found f sub x sub y. F sub x sub y. That's how it's done. Okay? And so now in that way, similarly, from this f sub y that we already found, think for yourself. Do you think you can understand what this symbol means? Okay? What is it telling you to do? What is it telling me to do? It's telling me to do the following, right from what we have already had, so, because now it's a new function, right? So right from what we have already had as a function of two variables, I'm going to take a further derivative in terms of y. The instruction is clearly written right here. So it's going to become, now so I'm targeting y here as a variable, so that here is coefficient. That's coefficient, okay, and that here is constant term. And so now my fyy here gives me just 2x plus 0, just 2x. Nice and easy. Okay, and then right from there, ladies and gentlemen, now let me introduce for you f sub yx. Okay, do you think you understand what this tells you to do? Okay, I think it should be easy enough for me so that I can skip telling you what that is. Okay, right from here, we take the partial derivative in respect to x. Right from this fy, we take a partial derivative in respect to x. Okay, so now in respect to x, now and then I have to erase the extra note here a little bit, because it's irrelevant at this point. In respect to x, that's coefficient. Okay, so we're looking at 2y plus 3x squared. That's how we're finding it. All right, so I'm leaving the results here, and I'll come back to this board, but that is how we find higher order partial derivatives. Okay, so a little bit about notation, because we're starting to get into higher order partial derivatives. So see, recall that fxx that I indicated earlier on the board. The order of the work I did is that it has to be the fx, and then we take the partial derivative in respect to x further. That's what it is. We take partial derivative in respect to x from an already found f sub x. That's why, and then f sub x itself here is another d. I mean, we can think of that, the function, we can think of the function z here. This function of two variable is a function of the f of x comma y to be a function z. Then this f sub x here can be regarded as a dz dx, as a partial derivative. And then on top of that, we take another d, okay, we take the partial derivative in respect to x again. So that's what this is for the outer level. The second level is here. The first level is inside. And so now the Leibniz symbol for this. So be careful a little bit that f of xx, yes, we're writing that as d, see, d and together, similar to we doing multiplication. It's not really a multiplication, but similar. It's d square z over dx squared. That's the Leibniz notation for second order partial derivative. And I carefully point out the order right there for you to understand. Okay, so the fyy is easy to understand. You can derive that similarly to what I've done here. Let's look at the fxy right here, fxy. And this is where it's important that you understand, otherwise it's easy to mix up the order. fxy here, it means from the found partial derivative in respect to x, we are going to find the second order partial derivative but in respect to y. So that's the order. So that has to come first and then the dy. Okay, but then the f sub x right here in Leibniz notation, we got dz dx, just like that. okay, because z is a function in equation format. Z is a function of x and y, and then the second level, the second order is partial derivative in respect to y. So when you're writing the Leibniz, notice how it's going a little bit opposite through here. That's d square z, okay, divided over dy dx. Look at how it's being a little bit backwards for here. That's my point I'm trying to point out right there. This is indicating the order from the right to the left. That comes first, that's second. This is from the left to the right, that comes first, that's second. That's what it is right there. But so these are one way of one convention of writing the symbols. The Leibniz convention is also a different way of writing the symbols right there. All right, that's what it is right there. So back on the result here, yes, this you can call this right here as the, this is, you can also regard to that. That's our final answer. But as far as symbol, d square z, okay, dx square. Okay. This one right here, that's the answer. But you can write in Leibniz convention d square z of dy square. Okay. This one right here, the order is important. See, it tells you to do y first and then x later. So here's d square z, okay, dy and then dx after. Okay, dy and then dx after. And then here on that I have, that's the answer. Okay, here we're looking at d square z. Okay, but then we take the x first, so dx on the right underneath the fraction bar right there, and then dy to the left. That's how it is. All right, so that's introduces the convention. So now when we're starting to talk about higher order derivatives, my demonstration examples here, in this example here, I stopped at the second derivative, but that doesn't mean that's all we have. So from this function you can find f x x y, f x y x, third derivative, and in whatever the partial derivative that is. There are so many of them that I don't even bother bringing it out anymore. You can go ahead and explore these on your own. Right there, third derivative. I mean, we shouldn't be limited to second order only. Okay, and so now, right from the demonstration example that I've given, we had that function xy squared plus x cubed y. Okay, and we found all the way down to fxy being 2y plus 3x squared. We found for ourselves our fyx. See, the order of the partial derivatives got switched, right? It's two different orders. So namely, or technically, they're different things. But this thing here gave me, from the previous results, 2y plus 3x squared. So now if we're looking at the two results here together, all of a sudden we realize, and this is an informal proof. Don't take me wrong, this is not a formal proof. There's a nice proof that's presented in any of your calculus textbooks that you're using. Doesn't matter what school you're taking this with. Okay, and doesn't matter what textbook you're using. Tomorrow or next term, your department may change to a different textbook, but this result will be exactly the same, and the proof will be given exactly the same. But it's not what I'm doing here. What I'm doing here is only to explain. Okay, but the formal proof can be found in any textbook. But now, what do we realize here as a generality? It's right from this example. Hey, wait a minute. We recognize fxy is equal to fyx. And yes, so now the truth I was about to say is, it's not only true for this example, for this particular problem, it's true for all functions out there. F of xy equals f of yx. Okay, very important to understand. So now it becomes a theorem. Okay, f of xy equals f of yx, as long as the second derivative, okay, are continuous. Okay. On a disk, on some disk D. The disk D right here, I'm talking about just some domain of our function. All right, so this is the highlighted result for that. It didn't even have to be that wordy.